Welcome to the Code Navigators. We're your guide for systematically getting through the language of the International Code Council books.
Yeah, navigating these codes can be pretty challenging.
Absolutely. Our mission is really straightforward. We go through the ICC codes chapter by chapter. We explain what's in them, focus on how you can find information efficiently.
And, crucially, help you get ready for those ICC certification exams. That's a big part of it.
It really is. We work on the idea that, being fluent in the code's specific language, that's just non-negotiable. It's key for actually using the code and for passing the tests.
Definitely. Fluency is the goal.
And we want to be upfront about how we create this program. We do use AI to help generate the content.
But, and this is important, every single detail, every technical point is checked, verified, and polished by a human code professional.
Right. Ensuring clarity and, most importantly, accuracy.
Which brings us straight to, well, probably the most critical instruction you'll hear today or maybe any day when you're studying the codes.
We have to start with a very important legal disclaimer. Let's be absolutely clear. This content, it's strictly for educational and informational purposes only.
That's right. It's designed just to help you understand how the code documents are structured and the concepts within them.
This program isn't professional advice. It's not an endorsement, and it's certainly not an official legal interpretation.
You absolutely must always consult the current official code book, the one published by the ICC.
And for any specific project, any design question or compliance issue, you need to get direct advice from a qualified professional.
We talk about the code, we don't interpret it for your project or enforce it. That distinction is, well, it's fundamental. It's our necessary starting point.
Okay, with that essential ground rule set, let's talk about today's focus. We are diving into the absolute bedrock of the 2021 International Building Code.
IBC Chapter 2, titled Definitions.
Chapter 2, the dictionary, right?
Well, yes and no. It's much more than just a dictionary. If you're new to the IBC, or if you're prepping for, say, the structural or plan review exams, this chapter is critical. Honestly, maybe the most critical.
How do you say that?
Because if you mix up terms, like if you think a firewall is the same as a fire barrier, or you confuse a dwelling unit with a sleeping unit.
Uh-oh.
Yeah, everything that comes after requirements in Chapter 5 on area, Chapter 10 on egress, you name it, it all falls apart. The requirements become, well, meaningless if you start with the wrong definition.
So it's not just about knowing the words, it's like a technical contract, the foundation for everything else.
Exactly. A technical contract is a good way to put it. We're going to explore not just what these terms mean, but also what actually happens in the real world when these definitions get applied.
And maybe look at some common traps, things that trip people up on exams or cost professionals time and money.
Precisely. We'll look at those semantic traps. So let's start with how the chapter itself tells you how to use it. Section 201, General Provisions.
Okay, Section 201, how does it guide us?
Well, right off the bat, the user notes make the main purpose clear. Chapter 2 provides a very precise technical definition for every single word or term that carries a specific technical requirement or a compliance mandate later in the code.
So its job is to eliminate ambiguity.
Exactly. No guesswork allowed. If you're reading Chapter 5 on, say, allowable building areas, and you hit the term fire separation distance.
You flip back to Chapter 2, and it gives you the official, measurable definition of that exact phrase.
That's the process. And Section 201 lays out the ground rules for using the whole document. Rule number 1 is 201.1 scope.
Okay, scope. What's the gist?
It basically says that the definitions here in Chapter 2 apply throughout the entire IBC, unless, and this is the exception, unless a later chapter specifically defines a term differently for its own context.
So Chapter 2 is the default authority, the baseline.
It's the baseline, yes. Now, 201.2 interchangeability is in there too. It talks about singular and plural, masculine and feminine genders being interchangeable.
That sounds more like a legal boilerplate, maybe, for drafting efficiency.
Pretty much. It clarifies grammar in a technical context, but for studying, the next rules are more about practical navigation, especially the idea that the codes are all connected.
Okay. So rule number 3?
201.3, terms defined in other codes. This is a huge navigational tip, really. It acknowledges that the IBC isn't alone. It's part of a whole suite of I-codes.
Like the plumbing code, mechanical code, fire code?
Exactly. So if you're reading the IBC and you run into a term that's not defined here in Chapter 2, maybe a very specific plumbing fixture term or something about mechanical ventilation.
The IBC itself tells you where else to look.
Precisely. It instructs you to look for the definition in the International Plumbing Code or the Fuel Gas Code, Energy Conservation Code, Fire Code, and so on. The relevant code for that term.
Okay, that seems like a really important tip. It prevents you from just searching endlessly within the IBC for something that isn't there.
Right. It tells you to look sideways into the other related codes. It's a common trap for students, actually.
Why is that a trap?
Well, people often study in silos. They think, I'm taking the IBC exam, so every answer must be in the IBC. But the code itself tells you that's not true for certain specialized terms.
Can you give an example?
Sure. Let's say you're figuring out ventilation for a hazardous material storage room. The IBC might point you directly to the International Fire Code to define terms like ventilation capacity or maybe exhaust velocity.
Yeah.
Those details are in the IFC, not the IBC.
Got it. So check Chapter 2 first. If it's not there, check 201.3 to see if it points you to another code. What if you strike out completely, it's not in Chapter 2, and it's not defined elsewhere?
That brings us to the rule of last resort. 201.4 terms, not defined.
Okay, what happens then?
In that pretty rare situation, the code says the term should have its ordinary accepted meaning, like the dictionary definition, essentially, or sometimes a meaning that's established by methods authorized in that specific code section you're reading.
So it falls back to plain English, but only as a last option.
Exactly. And the fact that it is the last rule tells you how seriously the ICC takes using its specific defined technical language. If you find yourself relying on ordinary meaning, you're probably operating a bit outside the core code requirements anyway.
You also mentioned something about a code development reminder near this section. Why does understanding how the code is made matter when we're just trying to read the definitions?
Good question. It matters because it gives context to why these definitions have such authority. That reminder points out that these definitions aren't just pulled out of thin air.
They come from a process.
A very rigorous one. They're the result of intense, dynamic, often public debates within the Code Development Committee structure. Experts argue, propose changes, refine the language.
So knowing that, say, the exact wording of accessible route was debated and finalized by experts.
It means the definition carries real technical weight. Every word was chosen carefully, intentionally. It underscores why just memorizing isn't enough. You need to understand the intent behind that specific wording.
That makes sense. It's not arbitrary. And let's move into some of the really critical terms, the ones dealing with life safety and how people use and get out of buildings.
Yes, life safety and occupancy.
Yeah.
Getting these definitions right, well, it can be the difference between a compliant design that gets approved and a project that fails inspection. Huge stakes.
Let's start with accessibility. There seems to be a cluster of related terms there.
There is. We need to master this sort of interconnected triangle of terms. We start broad with just accessible.
Accessible, what does that cover?
It refers generally to a building or a facility or even just a part of one that complies with the accessibility rules in Chapter 11 of the IBC. It's the overall state of compliance, you could say.
Okay, so that's the big picture. Then it gets more specific.
Right. Next is accessible route. This is defined as a continuous, unobstructed path that connects all the accessible elements and spaces within a building or facility and connects them eventually to a public way.
So route describes the actual physical path. Continuous, no barriers.
Exactly, the pathway itself. But then for life safety planning, the absolute crucial term is accessible means of egress.
Okay, accessible means of egress. What makes this one so specific?
It's highly specific. It's defined as a continuous and unobstructed way of egress travel. So far, similar. But it has to comply not just with Chapter 10 on egress, but specifically with the very detailed requirements found in the ICC A117.1 standard.
The A117.1 standard. That's the key link, isn't it?
That's the crucial distinction. The IBC tells you what spaces need to be part of an accessible means of egress, but it's the A117.1 standard that's an ANSI standard, very detailed, that specifies how.
Like ramp slopes, handrail dimensions, clear widths, all the nitty-gritty technical specs.
Precisely. All the things needed to make that egress path actually usable by someone with a disability during an emergency. Things like areas of refuge, specific exit and closure requirements, they all tie back to A117.1 when it's an accessible means of egress.
So if you're doing plan review, you absolutely have to remember that link. Accessible means of egress means you have to open up A117.1 and apply its rules.
You got it. That's a key takeaway for exam prep.
Okay, let's broaden out again to the overall structure of getting out of the building. The means of egress. The definition seems to break it down.
It does. The core definition is simple, but really powerful. It must be a continuous and unobstructed path of vertical and horizontal egress travel
Continuous and unobstructed.
from any occupied point in a building or structure all the way to a public way. Those two words, continuous and unobstructed, are the absolute standard. No breaks, no blockages allowed.
And this means of egress has three distinct components that everyone studying needs to memorize, right?
Yes, absolutely fundamental. They are exit access, the exit itself, and the exit discharge.
Okay, let's take them one by one. Exit access.
Exit access is the start of the journey. It's the part of the means of egress path that leads from any occupied portion of the building to the entrance of an exit.
So like the room you're in, the open floor area, maybe the corridor leading towards the stairwell.
Exactly. It's the initial path towards safety. Then you reach the exit.
And the exit is a protected part.
Generally, yes. Think of a fire-rated stairwell or an exit ramp, maybe an enclosed exit passageway. It's the component designed to protect occupants from fire hazards in the rest of the building while they continue their egress travel.
Okay, so exit access leads you to the exit. The exit protects you through part of the building. And then?
Then you have the exit discharge. This is the final leg, connecting the end of the exit component to the ultimate safe destination, the public way.
And public way also has a definition, doesn't it? It's not just any open space.
Correct. A public way is defined specifically as a street, alley, or similar parcel of land that's open to the outside air, deeded or dedicated for public use, and has a clear width of not less than 10 feet. It has to lead somewhere safe, or essentially off the property or to another street.
10 feet minimum width. Okay. Now, within the exit access part, the code gets really specific about pathways, differentiating between corridors and what was the other one? Aisle access ways.
Yes, corridor versus aisle access way. This is a really important distinction and honestly a common point of confusion, especially when dealing with assembly occupancies like theaters or lecture halls.
So what's a corridor?
A corridor is defined as an enclosed exit access component that provides and defines a path of egress travel. The key is typically that it's enclosed by walls and it leads towards an exit or another part of the exit access.
Enclosed path. Got it. And an aisle access way. How is that different?
An aisle access way is distinct. It's defined as the initial portion of an exit access path that leads directly to an aisle. Think about a movie theater again.
Okay.
The short path between the rows of seats, the path you walk along the row to get to the main aisle, that's the aisle access way.
Ah, I see. It feeds into the main aisle.
Exactly. And the code puts very strict limits on how long that aisle access way can be. It has to lead directly to a compliant aisle, which then leads towards the exit access or exit. The requirements for fire ratings, widths, length, they're completely different for a corridor versus an aisle access way.
Okay, that's a critical difference. Mixing those up could lead to major design errors.
Absolutely, especially with travel distance calculations in Chapter 10.
All right, let's shift gears from movement out of the building to how people live in the building. Occupancy definitions. We start with the basic building.
Building is defined very broadly. Pretty much any structure that's built or used for shelter or support of any kind of occupancy. Simple enough.
But then it gets tricky with dwelling unit versus sleeping unit. What's the core difference there? Because the consequences seem huge.
They are huge. The dwelling unit is basically the definition of a permanent home or apartment. The key phrase is that it's a single unit providing permanent provisions for 4 specific functions: living, sleeping, eating, cooking, and sanitation, bathroom facilities.
All 4 must be inside that single unit: living, sleeping, cooking, sanitation.
All 4 contained within the unit intended for permanent type living. That's a dwelling unit.
Okay, so what's a sleeping unit then?
A sleeping unit, by contrast, is a room or space where people sleep, but it lacks one or more of those permanent provisions found in a dwelling unit.
So maybe it has a bed and a bathroom, but no kitchen. Or maybe the bathroom is shared down the hall.
Exactly. Common examples are hotel rooms, motel rooms, dormitory rooms, maybe rooms in an assisted living facility where cooking or sanitation facilities are shared or located outside the individual unit. It's primarily for sleeping.
And the consequence of that difference, why does it matter so much if it's called a dwelling unit or a sleeping unit?
Oh, it changes everything. Think about fire separation requirements between units, the required travel distances in corridors, the type of fire alarm system needed, sound insulation between units.
It all hinges on that definition.
Pretty much.
Yeah.
A building full of dwelling units is typically classified as occupancy group R2, residential, permanent. A building with sleeping units might be R1, residential, transient, like hotels, or maybe even certain types of R2 or I1, institutional, depending on the specifics. The code requirements for R1 versus R2 are vastly different in many areas.
That brings us neatly to the definition of how long someone stays. Transient.
Right. The code puts a number on it. Transient is defined as occupancy of a dwelling unit or sleeping unit for not more than 30 days.
30 days, that's the magic number, the bright line in the sand.
That's the bright line. If a place is designed for transient occupancy, like a hotel or one, but someone ends up staying for, say, 31 days.
They technically become a permanent resident under the code's definition.
Technically, yes. Their occupancy shifts from transient to permanent. And that shift, just based on duration, could potentially trigger requirements more typical of an R2 occupancy.
Like what? What might change?
Well, maybe increased sound transmission class. STC ratings are required between units in an R2, which aren't typically needed in an R1 hotel. Or maybe the fire alarm system monitoring requirements change. It can have real compliance implications if a building's use drifts from transient to permanent without the design reflecting that.
Wow, okay, so that 30-day definition is really powerful.
It is. Finally, in this section, let's touch on change of occupancy. This sounds like it could be a regulatory minefield.
Yeah, when does the code say an occupancy has officially changed?
The code lays out three main scenarios that constitute a change. One is pretty obvious, a change in the actual use of the structure, like turning an office building into apartments, residential to commercial, or vice versa.
Okay, straightforward enough. What's the second?
Second is a change where the new use represents a different level of hazard or risk compared to the old use. Even if it stays within the same broad occupancy group, if the specific hazard level increases significantly, that can be deemed a change of occupancy requiring upgrades.
So maybe changing a regular retail store into one that sells hazardous materials.
That could potentially trigger it, yes. And the third scenario is a bit more subtle.
What's the third one?
It's defined as any alteration to a building or structure that results in the structure having to comply with the code requirements for the new occupancy classification.
Any alteration that mandates compliance. That sounds a bit circular or maybe like a catch-all. How should people understand that?
It's kind of the code's way of ensuring that safety doesn't get eroded through lots of small incremental renovations over time.
Yeah.
If you undertake a significant alteration.
Significant enough that it forces you to meet current code requirements for that specific part you're altering, like maybe upgrading an egress stair.
Right. Sometimes that mandated upgrade for one element can be deemed significant enough by the building official to trigger a reevaluation of the entire occupancy classification based on the current code, not the code it was originally built under.
So a major renovation could force the whole building up to current code standards for its use.
It can, yes. The code is structured to prevent owners from doing minimal compliance changes piece by piece, to avoid bringing an older building up to modern safety standards when significant work is being done anyway. It's about maintaining safety over the life of the building.
Okay, that's a really important concept to grasp. Let's move on to the materials themselves, the stuff buildings are actually made of. Structural integrity starts here, right? Chapter 2 seems very detailed on materials.
Extremely detailed, especially for fundamental materials like masonry. It forms the literal foundation for so many structures.
So what's the basic definition of masonry?
The general definition is pretty broad. Built-up construction or combination of materials like clay, shale, concrete, glass, gypsum, or stone units bonded together, usually with mortar.
But then it breaks down into different types based on how they're put together.
Exactly. There are 4 main technical classifications, and which one applies directly impacts how you calculate its structural capacity.
Okay, what's the first type?
We start with the simplest, solid masonry. This means the masonry units are laid close together and any internal spaces are completely filled with mortar or grout. Essentially, no unfilled voids or spaces within the constructed element. It forms a homogeneous mass.
Solid, makes sense. What's next?
Next is grouted masonry. Here, the interior cores, or spaces within the masonry units, or the spaces between multiple layers, withes of masonry, are deliberately filled with grout.
So you're intentionally filling the voids. Why?
Often it's done to increase strength, improve fire resistance, or, very importantly, to embed steel reinforcement.
Which leads us to the next type.
Precisely. Reinforced masonry. The key distinguishing factor here is the design intent. It's masonry construction, where steel reinforcement, typically rebars placed within those grouted cells or spaces, and the tensile strength of that steel is actively considered and relied upon in the structural design calculations.
So you're counting on the steel to help carry the load, specifically tension forces.
Exactly. The steel resists the pulling forces that masonry itself is weak against.
And the opposite of that would be?
Unreinforced plain masonry. Here, the structural design relies solely on the masonry unit's ability to resist compressive forces and whatever minimal tensile strength the masonry and mortar themselves have.
So even if there happens to be some steel in there for, say, crack control, you're not counting on it for the main structural load resistance in the calculations.
Correct. Any steel present is either minimal or it's specifically ignored in the design calculations for resisting tension or bending.
Mm.
Knowing whether a wall is designed as reinforced or unreinforced is absolutely fundamental to determining its load-bearing capacity.
Okay, masonry covered. Let's switch to wood. The code seems to be adding terms for newer engineered wood products, like mass timber. That's becoming more common, isn't it?
It is, yes, especially in taller wood buildings. The code defines mass timber pretty broadly to capture these new systems. Its structural elements, made primarily of wood, could be built-up pieces, large panels, or other engineered configurations that are intended to be used in both vertical, like walls, and horizontal, like floors and roofs, load-resisting systems.
So it covers things like cross-laminated timber, CLT, nail-laminated timber, NLT, those big, thick wood panels.
Exactly. That definition is crucial because later chapters, especially those dealing with fire resistance for new tall wood building types, like type IVA, BC, rely entirely on this foundational classification.
And within that broader category, we still have traditional engineered wood, like glued laminated timber or glulam.
Oh yes, glulam is a classic. The definition is very specific. It's a structural timber product manufactured by bonding together individual pieces of wood laminations or lams with adhesives, where the grain of all the lams runs parallel.
So it's an engineered composite designed for higher strength and consistency than you might get from a single solid piece of timber.
Precisely, distinct from just regular dimensional lumber.
And how is standard lumber defined?
Lumber is defined based on its properties, primarily its nominal size, like a 2x4, 2x6, its assigned grade, which reflects its strength and quality, and its seasoning or moisture content. The definition points towards established grading rules, like those from the American Lumber Standard Committee.
So the definition ensures that when an engineer specifies, say, #2 grade Douglas fir lumber, everyone knows exactly what strength properties they can count on for calculations.
That's the goal: uniformity and predictability for structural design.
Okay, let's move to concrete. The basic definition seems simple: aggregate, cement, water. But the type of aggregate makes a big difference, right?
Right.
Especially with weight.
A huge difference. The weight of the aggregate dramatically changes the concrete's properties, affecting everything from structural load calculations, especially seismic loads, to fire resistance ratings.
This is where we get the difference between regular concrete and things like lightweight concrete.
Exactly. Lightweight concrete, specifically lightweight structural concrete, uses special aggregates like expanded shale, clay, slate, or slag to produce concrete with a significantly lower density. The definition usually pegs its oven-dry unit weight somewhere between 85 and 115 pounds per cubic foot PCF.
Compared to normal weight concrete, which is around 145, 150 PCF.
Right. That weight reduction is a major advantage in reducing the overall mass of the building, which is really beneficial for seismic design. Less mass means less inertial force during an earthquake.
Then there's also sand lightweight concrete. How's that different?
Sand lightweight concrete is sort of a hybrid. It uses lightweight coarse aggregate, but replaces the lightweight fine aggregate with natural sand. This makes it a bit heavier than pure lightweight concrete, usually in the range of 105 to maybe 120 PCF.
Why do that? Why not just use all lightweight aggregate?
It's often a balance. You still get significant weight reduction compared to normal concrete, but using natural sand can sometimes improve workability, finishing characteristics, or achieve slightly higher strengths more economically.
Okay. And then there's a really specialized one, perlite concrete. What's the deal with perlite?
Perlite itself is a type of volcanic glass. When you heat it rapidly, the water trapped inside turns to steam and expands, causing the glass to pop like popcorn into tiny, lightweight cellular beads.
So perlite concrete uses these popped glass beads as aggregate.
Yes. It makes the concrete extremely lightweight. Unit weights can be down around 30 PCF or even lower. But it's generally not used for structural purposes because it doesn't have much strength.
So what's it used for?
Primarily as an insulating material. You often see it used in non-structural roof fill or floor fill, or sometimes in fire-rated assemblies, specifically for its excellent insulating and fire resistance properties, not for load-bearing capacity.
Got it. Lightweight for insulation and fire rating. Okay, let's transition to fire protection systems and features. These definitions seem absolutely critical for life safety. Getting them wrong could be catastrophic.
Couldn't agree more. When we talk life safety, the fire protection definitions are non-negotiable. You absolutely have to differentiate between different types of systems and different types of barriers. The consequences for mistakes here are, well, severe.
Let's start with the systems that put out fire's active suppression. The most common one is probably the automatic sprinkler system.
Right. The definition focuses on its function. It's an integrated system of underground and overhead piping connected to a water supply. It's designed so that when the system detects heat from a fire, it automatically activates and discharges water over the fire area.
And the definition lists the key components: piping, water supply, control valves, sprinkler heads.
Yes, all designed to function automatically, based on the sprinkler head activating at a certain temperature.
Now, the code uses a broader term too: fire protection system. How does that relate?
Fire protection system is the umbrella term. It covers all devices, equipment, and systems used to detect a fire, activate an alarm, suppress or control a fire, extinguish it, or manage smoke. Sprinklers are just one type of fire protection system. Fire alarms are another. Smoke control systems are another.
Okay, so sprinkler system is a specific type under the big umbrella. What about automatic fire extinguishing system? Sounds similar to sprinkler system.
It's a broader category than just sprinklers. An automatic fire extinguishing system refers to any system that's designed to automatically detect a fire and discharge an approved extinguishing agent to suppress or put out the fire.
So the agent doesn't have to be water.
Exactly. It could be a clean agent gas, like in the server room. It could be chemical foam, like for flammable liquid hazards. It could be dry chemical powder, or it could be water, including sprinklers or water mist. It's a general category for automated extinguishing systems.
Which brings us to automatic water mist system. That sounds like a specialized water system.
It is. It's a relatively modern technology defined as a system using very fine water sprays of mist. It requires special discharge nozzles operating at specific pressures, often much higher than standard sprinklers, to create these tiny droplets.
And how does mist work differently than regular sprinklers?
It suppresses fire through a combination of effects, primarily cooling the fire plume and the surrounding air, and also by displacing oxygen as the fine water droplets turn rapidly into steam near the flames. It often uses significantly less water than traditional sprinklers, but requires very careful engineering design specific to the hazard being protected.
Okay, different technology, different application. Now let's shift from systems that put out fire to features that contain fire. And this is where we hit that major confusion point you mentioned earlier: firewall versus fire barrier.
Yes, this distinction is absolutely fundamental, especially because it dramatically affects how you calculate allowable building size and height in Chapter 5. Getting this wrong is a very common and costly mistake.
So let's break it down. What's a fire barrier?
A fire barrier is the, let's say, more common type. It's defined as a vertical or horizontal assembly, like a wall or a floor ceiling assembly, that's fire resistance rated and designed to restrict the spread of fire. It subdivides spaces to create compartments.
So it has a fire rating, like 1 hour or 2 hour?
Yes, and it has requirements for protecting openings, like fire doors or fire dampers. But crucially, a fire barrier typically relies on the main building structure for its support. If the adjacent structure collapses, the fire barrier likely goes with it.
Okay, relies on the building structure. How is a firewall different then?
A firewall is structurally unique. The definition highlights 3 mandatory characteristics. First, like a barrier, it must be fire resistance rated, often for a longer duration, like 3 or 4 hours. Second, it must be continuous from the foundation all the way up to or through the roof. And third, this is the absolute key, it must be structurally independent.
Structurally independent. What does that mean in practical terms?
It means the firewall is designed and built to maintain its structural integrity and stay standing, even if the entire building structure on either side of it completely collapses due to fire or other causes. It has its own foundation and structural support system.
Wow. So it can stand on its own even if the rest of the building burns down next to it.
That's the design intent. And that structural independence is why it has such a massive impact on building size calculations. If you build a compliant firewall right down the middle of a large building.
The code often lets you treat the two halves as separate buildings.
Exactly. For the purposes of calculating allowable area and sometimes height limitations under Chapter 5, a proper firewall effectively creates 2 independent buildings on the same lot. This can allow for much larger overall structures than would otherwise be permitted. That's the big payoff for the added cost and complexity of building a true firewall.
Okay, that structural independence is the game changer. Got it. What about protecting against fire spread between buildings? That's fire separation distance, right?
Yes, fire separation distance is the term used to define how far away a building's exterior wall is from a potential fire exposure source outside the building. This distance is critical because it dictates how much unprotected opening area, like windows and doors, you're allowed to have in that exterior wall, based on tables in Chapter 7.
And how is that distance measured? It's not always just to the property line, is it?
Correct. The definition gives three potential measurement points. It's measured perpendicular from the face of the exterior wall to 1, the center line of an adjacent street, alley, or public way; 2, an imaginary line drawn equidistant between two buildings that are on the same property lot; or 3, the actual property line, lot line itself. Whichever applies dictates the required fire resistance and opening protection for that wall.
Okay. And when we have these rated walls and floors, barriers, or even firewalls, we inevitably need to poke holes in them for pipes, wires, ducts. How does the code address that?
That's where the penetration fire stop comes in. It's defined as an assembly or material installed within or around an opening of penetration through a fire resistance rated assembly, like a wall, floor, or ceiling.
And its job.
Its job is to restore the original fire resistance rating of that assembly that was compromised by making the hole. It seals the opening to prevent the passage of flames, hot gases, and smoke through the penetration point.
So using the right tested fire stop system is crucial. Otherwise, the hole just negates the rating of the whole wall.
Absolutely. Improper or missing fire stopping is a major code violation. It completely undermines the compartmentalization strategy. The definition emphasizes it has to be an approved system tested to specific standards, like ASTM E814 or UL 1479.
Makes sense. Okay, shifting to hazardous materials, specifically liquids. What's the key difference between flammable liquids and combustible liquids? It seems to come down to one number.
It does. It all hinges on the liquid's closed cup flash point. That's the lowest temperature at which the liquid gives off enough vapor to form an ignitable mixture with air near its surface.
So flammable liquids.
Flammable liquids are defined as those having a closed cup flash point below 100 degrees Fahrenheit, which is about 38 degrees Celsius. These are classified as Class I liquids.
And they're considered more dangerous.
Generally, yes, because they can produce ignitable vapors at or even below typical room temperatures. This Class I category is further subdivided into IA, IB, and IC based on combinations of flash point and boiling point. Class IA liquids, like gasoline or diethyl ether, are the most volatile and hazardous, with flash points below 73 degrees Fahrenheit and boiling points below 100 degrees Fahrenheit. They pose a significant vapor hazard.
Okay. And combustible liquids.
Combustible liquids are those with a closed cup flash point at or above 100 degrees Fahrenheit. They're less volatile than flammable liquids.
So they generally need to be heated up before they produce enough vapor to ignite easily.
That's the practical difference, yes. Combustible liquids are broken down into Class 2, flash point from 100 degrees air up to 140 degrees air and above. Class 3 is further split into IIA and IB. The higher the flash point, generally the lower the immediate fire hazard at ambient temperatures. These classifications dictate storage limits, ventilation requirements, and fire protection measures per the fire code.
Got it. Flash point is the key. Below 100 degrees AFR is flammable. Class 1, 100 degrees AFR and above is combustible. Class 2 and 3.
You nailed it. Lastly, in this hazard section, let's look at the definition of explosion. It's quite technical.
How does the code define an explosion? It's more than just a loud bang, right?
Much more. The definition focuses on the physics. It's an effect produced by a sudden, violent expansion of gases. This expansion can result from a rapid chemical reaction, like detonation of dynamite or ignition of flammable vapors, a sudden change in physical state, like a boiling liquid expanding vapor explosion or BLEVE, or even an atomic nuclear reaction.
And the key outcome is?
A rapid increase in pressure, a shock wave, and usually the release of high temperatures and flying debris. The definition needs to be technical because designing safeguards, like explosion venting or suppression systems, requires understanding the extremely rapid pressure rise and energy release associated with these events.
Makes sense. You need a precise definition to design precise protection. Okay, let's move into the final section outlined. Environmental conditions and the loads they impose on structures.
Right, these are fundamental concepts, especially for anyone involved in structural design or review or studying for those exams. We need to be clear on the different types of loads that buildings have to resist.
Let's start with the 4 basic load calculations mentioned. First up, dead load.
Dead load is essentially the permanent weight of the building itself. It includes the weight of all the construction materials, walls, floors, roofs, columns, beams, plus any permanently attached equipment, like HVAC units, plumbing fixtures, etc. It's static, it doesn't move.
Okay, the weight of the structure itself. Then we have live load.
Live load is the variable load. It's the weight produced by the use and occupancy of the building. This includes people, furniture, stored materials, movable equipment, anything that's not part of the permanent structure, but is expected to be there during the building's life.
So it changes depending on how the space is used. An office live load is different from a library storage live load.
Exactly. Chapter 16 provides minimum required live loads for different occupancies. There's also a specific subset called roof live load.
How is that different from just live load on the roof?
Roof live load specifically refers to temporary loads during maintenance or repair imposed by workers, equipment, and materials placed on the roof. It's calculated separately from and often exclusive of other loads like snow or wind.
Okay. Dead load, live load, roof live load. What's the fourth category?
The environmental loads.
Uh-huh.
These are the loads imposed on the building by nature. Wind loads, snow loads, rain loads, especially ponding on flat roofs, flood loads, like hydrostatic pressure or wave action, and earthquake, seismic loads. These are highly dynamic and very dependent on the building's geographic location and local climate.
So engineers have to calculate all these different loads acting in the building.
Yes, and they have to combine them in various ways specified in Chapter 16 to determine the worst-case scenarios for design. To ensure safety, they don't just use the raw calculated loads, they apply factors. One key factor is the load factor.
Load factor, what does that do?
A load factor is a multiplier applied to the nominal load, the calculated dead load, live load, wind load, etc. Its purpose is to account for uncertainties, the fact that the actual loads might be higher than calculated, and also for the low probability that multiple extreme loads, like maximum wind and maximum snow, will occur at the exact same time.
So it basically increases the load that the structure has to be designed to resist, building in a safety margin on the load side.
That's exactly right, especially in load and resistance factor design, LRFD, which is common now.
And that works together with factors applied to the material's strength.
Yes. On the other side of the equation, you have the strength of the materials and components. Chapter 16 often refers to nominal strength, the theoretical capacity based on material properties, and then applies a strength factor, also called a resistance factor, phi factor.
And the strength factor does the opposite of the load factor.
Correct. The strength factor is always less than 1.0. It reduces the nominal strength to account for uncertainties on the resistance side, things like variations in material quality, potential flaws in manufacturing, and tolerances in construction.
So load factors increase the required strength, the demand, and strength factors decrease the available strength, the capacity. The structure is safe if the factored resistance is greater than or equal to the factored loads.
That's the fundamental principle of LRFD design. It ensures a reliable safety margin. For exams, understanding the purpose of load factors versus strength factors is key.
Okay, good clarification. Now let's turn to specific environmental hazards defined in Chapter 2. Flood risk first. How is a flood hazard area defined?
A flood hazard area, sometimes called the floodplain, is defined based on probability. It's the land area that's subject to a 1% or greater chance of flooding in any given year.
That's what people often call the 100-year flood.
Exactly. It doesn't mean it floods only once every 100 years, but that there's a 1 in 100 chance of reaching that flood level in any specific year. These areas are typically mapped by FEMA on flood insurance rate maps, firms.
And if you're building in that area, the critical number you need is the design flood elevation, DFE.
Absolutely critical. The DFE is the required elevation, usually referenced to a standard datum like NAV 88, to which the lowest floor of a building, including the basement, must be elevated or flood-proofed.
And it's not just the base flood elevation from the map, right? It includes extra height.
Correct. The DFE is typically the base flood elevation, BFE, shown on the firm, plus an additional height called freeboard. This freeboard, often 1 or 2 feet, sometimes more depending on local rules or the building's risk category, provides an extra margin of safety above the theoretical 100-year flood level. It dictates how high you have to build.
And materials used below that DFE have to be special.
Yes, they need to be flood damage resistant materials. The definition is materials that are capable of withstanding direct and prolonged contact with floodwaters without sustaining significant permanent damage.
What kind of damage are we talking about?
Things like swelling, warping, decomposition, mold growth, loss of structural integrity. The code, often referencing FEMA technical bulletins, lists materials considered acceptable, like concrete, solid masonry, corrosion-resistant steel, and unacceptable, like standard drywall, untreated wood, carpet, for use below the DFE in enclosed areas.
Okay. Let's shift from water to shaking. Seismic risk. The overall classification seems to be the seismic design category.
Right. The seismic design category, SDC, is a classification assigned to a structure based on two things: the severity of the expected earthquake ground motion at the site, determined from maps in the code or ASCE 7 standard, and the building's assigned risk category.
Risk category. How is that
The
determined?
risk category, ranging from I to IV, is based on the building's use and the potential consequences if it fails during an earthquake.
Can you break down the categories?
Sure. Category 1 is for buildings with low risk to human life if they fail, like agricultural storage sheds. Category 2 is the standard for most typical buildings, offices, stores, houses, where failure could cause substantial economic loss and potential injuries, but not mass casualties.
Okay. What about Thur and 4?
Category 3 is for buildings representing a substantial hazard to human life if they fail. This includes places with large numbers of people, like schools, theaters, or buildings whose failure could impact essential facilities. Category 4 is reserved for essential facilities themselves.
Essential facilities, meaning?
Hospitals, fire stations, police stations, emergency communication centers, power generating stations, buildings that absolutely must remain standing and functional during and immediately after a major earthquake to provide essential services for disaster response and recovery.
So the higher the risk category, the more stringent the seismic design requirements, leading to a higher seismic design category overall.
Exactly. A hospital, risk category 4, in a high seismic zone will be assigned a very high SDC, like D, E, or F, requiring much more robust structural systems than a warehouse, risk category 2, in the same location.
Now, the final definition you highlighted seems really interesting. Designated seismic system. You said this goes beyond just the main structure.
Yes, this is a critical point and often overlooked. A designated seismic system includes not only the primary structural elements designed to resist earthquake forces, like frames, shear walls, diaphragms,
But
but also specific non-structural components whose failure during an earthquake could directly impair the building's overall structural integrity. OR, very importantly, could jeopardize the function of life safety systems.
non-structural components, like what?
The definition explicitly mentions things like fire sprinkler piping supports, emergency power generator anchorage, critical HVAC equipment bracing, fire alarm control panels, even things like supports for heavy ceilings or partitions in essential facilities.
So the code recognizes that if the fire alarm panel falls off the wall during an earthquake or the sprinkler pipes break, that's a life safety failure just as critical as a column collapsing.
Precisely. The designated seismic system definition forces engineers and designers to consider the seismic resilience of these critical non-structural systems, ensuring they are properly braced, anchored, and protected so they can function when needed most during and after the shaking stops. It's a holistic view of seismic safety.
That's a really important insight. It's not just about the bones of the building. Okay, we've covered a lot of ground in Chapter 2.
We have. It's dense, but absolutely foundational.
So wrapping this up, we've systematically gone through the language of the 2021 IBC Chapter 2. We've tried to highlight not just the definitions themselves, but also the real-world application and the consequences of getting these terms right or wrong.
Yeah, I think the main takeaway for you, the listener, especially if you're studying, is that really mastering this chapter comes down to understanding the subtle differences.
Like firewall structural independence versus fire barrier restraint.
Exactly. Or knowing the specific flashpoint that separates a Class IA flammable liquid from a Class 2 combustible liquid. It's those nuances, those specific details embedded in the definitions where true compliance lies. And honestly, where success on the exams is often found.
Absolutely. Now, putting together this kind of detailed, expert-checked educational content, well, it takes a good amount of resources and effort.
It definitely does. We enjoy doing it, but it takes time and expertise.
So if you found this systematic exploration helpful, if it's valuable for your studies or your work, and you'd like to support us in creating more content like this for future chapters,
We'd certainly appreciate it. We encourage you to check out the Patreon link that you'll find in the show description. Any support helps us continue unlocking and explaining these code chapters.
indeed. Okay, let's leave you with a final thought to chew on, something to reflect on based on what we discussed today. If we accept that idea we just talked about, that the overall seismic safety of a building relies just as much on its designated seismic systems, including those non-structural parts like alarms and controls, as it does on the main frame structure.
Okay, accepting that premise.
Then what definition in the code, maybe one that seems really mundane or simple on the surface, actually holds the most surprising or significant implications for occupant safety when you view it through that seismic lens?
That's a great question. It makes you think beyond the obvious? Maybe. Maybe consider the definition of something like a suspended ceiling system, or even just how partitions are required to be attached or braced.
Things we don't normally think of as life critical.
Right. But if a heavy ceiling grid isn't properly braced as part of a designated seismic system in, say, a hospital corridor, risk category 3, its collapse could block egress or injure people. So the code, through these precise definitions and requirements, elevates seemingly minor components to life-critical status in certain situations. It forces you to consider how everything interacts.
Fascinating. Something to definitely mull over. Think about how seemingly simple definitions gain huge importance, depending on the context.
It's all interconnected.
Well, thank you for joining us on the Code Navigators.
Hope this was helpful.
We'll catch you next time as we continue our systematic navigation of the International Code Council books.